Last lecture, I talked about sketching and then concentration of measure and applications of it for dimensionality reduction. Specifically, we talked about Johnson-Lindström lemma. That is useful when you only care about pairwise distances between your data points. So the difference from other things we have seen, like PCA, is PCA tries to preserve the entire structure of data. Here, you only care about how far apart two data points are, okay? And you go from whatever dimension your data lives in to log of number of data points divided by epsilon squared, and there is some improvement on dependency on epsilon as well. And it's super easy. You just create a random matrix and project down everybody, essentially. Okay. Okay. But it was like kind of getting close to the end of the lecture when we talked about this. So I kind of skipped over how you obtain this part. Well, I talked about it, but we didn't complete it. So maybe I want to spend just 5 minutes to do that. So we talked about this Gaussian concentration. Let me also recall that. So what was that? If you go pick a random vector with n coordinates, and every coordinate is Gaussian with unit variance. In other words, your vector is Gaussian with covariance matrix identity. Okay, every coordinate is independent. They have unit variance. Okay, all right. Identity matrix means two coordinates does not have any correlation, right? Okay, very good. And in that case, turns out this vector concentrates around the place that the vectors have norm root n. So the vectors that has norm, say, square root of n, would be like, if you take the sphere, say vectors with norm 1, enlarge it to square root of 3, right? That's that. So this vector comes around it. Doesn't have to be precisely square root of n, of course, it's a random vector. What you're saying is like the norm of it minus square root of n bigger than epsilon times square root of n is less than a very small probability, okay? So with very high probability, close to 1, your vector will end up in this cell, which is about the vectors that has norm either 1 minus epsilon times square root of n, or at most 1 plus epsilon times square root of n. So this is kind of, non-trivial. We talked about how do you obtain this. I'll now use this to obtain the Johnson-Lindström that I talked about. Any questions about this one? So if you missed the last lecture on concentration of measure, this stuff might look strange. That's typical behavior in high dimensions. You get used to them after you see enough facts about it. So turns out higher dimensions is actually easier to handle. However, it's very different than our low dimensional intuition. You train your intuition. After that, you realize more dimensions is actually easier to predict than less. Very counterintuitive, I agree, but that's how it is. Okay, now let me use this Gaussian concentration to obtain that Johnson-Lindström I was talking about. So first we will take a random matrix, K times D, and we take a deterministic vector V that lives in RD, and we multiply A with V. Okay, so A is a K times D random matrix. So it has like A11, A12, A1D, and goes till AK1, AK2, AKD. And I have a deterministic vector here, V1, V2, VD. And when you do the dot product, you will end up getting a K-dimensional vector, right? Matrix is K times D. Vector is D-dimensional. The output will be K-dimensional. And let's just write the first coordinate of it. So how do I get the first coordinate? Multiply the first row here with your vector. Right? Very good. And that is A1, 1, V1, A1, 2, V2, up to A1, D, VD. I'll rewrite it here, and the other coordinates will come similar. So this is my first coordinate. So let's call this something. Let's call it Z. What is the expectation of Z? So these are just deterministic numbers. These are Gaussians with expectation 0 and variance 1. What will be the expectation of the whole thing? Expectation goes exactly like, so you can decompose it. It's a linear thing. So the expectation of this is 0, 0 times anything 0, 0, 0, 0. You will end up getting expectation is 0. Fine. How about the variance? Expectation of Z squared, since this A11, A12, yada yada are independent from each other, again, it's going to come out kind of nice. It's going to be like expectation of A11 squared, V1 squared, plus expectation of A12 squared, V2 squared. And it's going to keep going like this, until A1 D squared, VD squared. But now notice that these are just deterministic numbers. And this stuff, we know the expectation of A1 squared. It's literally a variance of it, which will assume to be 1. So from here, you'll just get this number out, and you'll have a 1 from the randomness. So at the end, the expectation of this vector, or this Z squared variance, comes precisely as V1 squared, V2 squared, VD squared. In other words, it is the norm of your vector squared. Right? And this is true for every single coordinate, not only first one. You can repeat the exact same idea. For every coordinate in the output vector, you'll get the same thing. Okay. Weird in a way, but also nice. Okay. And then if I divide it by, for the moment, just for the sake of discussion, if I divide this guy with the norm of V, then expectation will be 1, right? And in that case, the vector I'm getting, the k-dimensional output, I have k stuff here, and let's say I'm taking that vector and dividing it by this norm of V, okay? A times V is the output. For the moment, so think about the case I'm dividing it by norm of V to understand what's going on. Well, then this will be like first coordinate is divided by V. When I'm taking squares and expectation, I'll get this. So this random vector, I have a deterministic vector V. I have a random matrix. I multiply it. It gives me a vector. I just normalize it with the norm of my vector, whatever it was. Now you'll get a random vector out. Every coordinate will have variance 1, mean 0, and every coordinate is a Gaussian. Okay? And this becomes precisely what we talked about in the previous slide or previous note. You have a Gaussian vector, k-dimensional, unit variance every coordinate. And we know where it lands. It's going to land precisely in that thin shell with root k, right? So this guy will behave like this picture. So it's k-dimensional. Here it was n, that's going to be k. So it's going to for sure have norm about root k, very highly concentrated there. So then what do? Well, you multiply it with 1 over k, and you don't divide it by this v. You end up getting a norm right about v. Okay. So if I divide it by v, and if I did not multiply with this, it will be root k. If you divide it with 1 over root k, it becomes 1. If you multiply back with this, you'll get norm v. So certainly the thing you output will have a very similar norm to whatever your vector's norm was. And then to get the thing I showed you about any collection of data points, you simply use this estimate for every distance pair. You keep using it, you add it to each other, and you get what's called this Janssen-Lindström lemma or Janssen-Lindström flattening. Let me repeat what this says. You got n data points, n is huge, and their dimension is also big. Very typical situation. And then the application you care about is about similarity of the data points. Okay? So you care what is the distance between a point to another one for your model. Then what you could do, just create a matrix, random every entry Gaussian with unit variance. This is where your vectors were living, the high number of features they got. And here you need to pick something about the logarithm of the number of data points you got divided by epsilon squared. Epsilon is your tolerance for error, how much error you could tolerate, okay? And then the guarantee is with very high probability, the pairwise distances versus pairwise distances after the projection will be at most epsilon times that distance. So you're perturbing with epsilon. So if your application tolerates some error, and if you only care about similarities, do Johnson-Lindstrauss, then do your model. This way you're dealing with smaller vectors, you'll end up getting a similar output. This could happen if you're doing some classification problems, some clustering problem, stuff like that. All right, so that's, again, going through about the stuff we did in the last 10 minutes of last lecture. Today, I will start new things, of course. So as you see, the theme is like about dimensionality reduction. So this is chapter 20 in your textbook. I'll put the references on our canvas. So what we have done so far, we talked about using this probabilistic stuff for reducing dimension. And we did many things of that sort. We did, sketching, streaming, Johnson-Lindstrauss. Now I'll try to show you different tools in this toolbox. So depending on your application, you can remember, there was such a tool, and go back, look it up, and use it for solving whatever problem you care about, okay? So the first thing we saw very early on in semester about dimensional reduction was this PCA. So what is PCA? You take some data, you're actually projecting it down, then you're lifting it back up. So what do I mean by that? So suppose I have data with n features and capital N many. And when you do XX transpose, you get an n by n matrix. Then what do? We look at its eigenvalues or singular values. Then we pick the top D, then we project down. That's what PCA is, okay? But you don't only project down. You take your X, you put it down on top D directions, then you lift it back up to where it was living. Okay? So you first project, then you lift back up. But at the end, the image is always like a D-dimensional subspace. I'm trying to fit the best D-dimensional subspace. That's what PCA is. Or I'm trying to pick D directions, which preserves most of the variance. But this perspective is very useful. I'm first putting it down and then lifting it back up. So this is called encoder-decoder architecture. So you first take your data, you encode it with some process, then you put, suppose it's like latent space now, and then I put it back up where it was living. This is called decoding. And then after that, you put a loss function. So in our PCA, what was it? Going down, back up, then minus what it actually was, squared, mean squared error. So after decoding, you will put a loss function, then you will try to find your good encoder and decoder, okay? So PCA is the linear version of the story, but we don't have to do linear. You can also do nonlinear. The first thing people do is usually called bottleneck autoencoder. So this field also goes by the name representation learning, okay? So the idea is like, I got some data. I'm not really sure what feature I'm looking for. I just want to put data in a form that my models can do things better. So it's so vaguely, phrased. It's like, what do I even do with this? Okay. So this subfield of machine learning is called representation learning sometimes. Okay. But it's this particular thing called autoencoders. That's what I'm going to be talking to you about in the next maybe 10 minutes or so. That is essentially nonlinear PCA. So instead of projecting down with a linear and lifting back up with another linear. We will project down with a neural net, lift back up with another neural net. So here is a typical situation. Suppose your data was, just for illustration, say 4-dimensional, okay? And we like to put stuff in higher dimensions in this neural nets, you go up and then put it down. So here, from going here to say 3 or 2 dimensions, this is your encoder. And then after that, there's gonna be another neural net doing decoding, going from latent back up to a number of features your data had. And then you'll put a loss function on top and you will train this. So why do we do this like a bottleneck? Because if you don't push it, reducing the dimension, quite often it ends up just learning the identity function. It does nothing to your data. Okay, so it kind of overfits right away. So the architecture should be such that it at least limits the ability a little bit, so you don't get that overfitting catastrophe. All right, that's why bottleneck architecture is very typical. And here's some plots. This fashion minutes data set, this UCI repo. So what do we see here? For the moment, we are just talking about vanilla neural nets, multi-layer perceptron, nothing fancy. We just put layers on top of layers in the bottleneck architecture I said. So this is what I talked to you about so far. So on left-hand side, that's what you see. They just trained it with apparently just 20 epochs. And looks like 3 layers, etc. And in the second, for that neural net encoder, they use a convolutional neural net since they are dealing with images. Makes sense. And that's what you see in B. So basically what's going on is like you take an image data, which has a whole bunch of pixels in it, take it like a vector that way, then it's encoding it to a smaller dimension, then lifting it back up. But still it's smaller dimensional, just living in that big dimension. So that's the output from this fashion data set you see. And here they are doing a little more tricks. Again, they are training a multi-layered perceptron and a CNN, doing exactly what we were doing there. And what they do is like, they take that encoding thing and then do a 2-dimensional nonlinear plotting, which I will talk to you about. We will learn about this later. So this is a technique if you really have to visualize in 2 or 3D. You have like high dimensional data, you want to have an idea, like how does it look? That's a trick for that. I'll tell you what that is. Here what they're doing is like, they do what they did right there. And on top of what they had in that encoder, they're putting on this trick to visualize better, okay? Or to understand better. And that's then how does that thing look? Okay, so this is bottleneck autoencoder. All like standard libraries would have it. Keras seemed very easy for me on this when I was playing with this, but I don't have any strong opinions on it. Okay, so anything you like would do this. Somehow Keras API looked very easy to do autoencoders when I was using it on a project last year. Anyway, okay, so this is bottleneck autoencoder. The second type of autoencoder, again, pretty common, is called denoising autoencoder. What do? You add noise to your data deliberately. And turns out it forces your autoencoder to learn the structure of data. Funny enough, okay? Adding noise turns out to be helpful. Normally, you're adding noise, you expect things to go bad. So since we are trying to reduce dimension in this autoencoding business, turns out like when you add some noise, when it tries to reduce the dimension, it ends up capturing structure of the data. I'll tell you a little more precisely what does that mean. So, but basic structure of denoising autoencoder, you add some noise to your data, you get to pick how much noise you're gonna add, that's your variance. Usually it's not so big. If you add too much noise, it will actually kill it. Okay, so you'll add some juice, not so much juice. Okay, and then you pass it through your autoencoder architecture. You do epoch after epoch, you train it. Then when you're gonna use it, you turn off the noise. You just put the data in, do the inference, reduce the dimension. Okay, because I was working with a student, he was training all these denoising autoencoders, not getting anything out of it. Like a month later, I realized he was forgetting to turn off the noise in the inference. So that's important. Okay? So you just put the noise in training. When you're going to actually use it, don't put more noise on top of what you already have. Okay, so that's a denoising autoencoder. And this is, again, some plot denoising autoencoders. Let's see what they're doing. So they do just vanilla multi-layer perceptron. And they add here Gaussian noise, here Bernoulli noise. Bernoulli noise is kind of extreme, though. You're adding a discrete noise. Okay. So unless your thing is very discrete, it's not a great idea, and you can see the results, of course. Okay. These are pictures from our textbook. I'll put the reference on Canvas, of course. Now, what I wanted to say, which is more interesting, is here. So this is a very interesting paper from back in the day, about 10 years ago. What they figured out is this. Suppose this colored part is our actual data. It's got some structure to it, okay? It's either 2D, but it's all on a curve, or like 3D on a surface, okay? It's got some structure to it, okay? So this is like a reasonable assumption for a lot of people. What is that assumption? Your data, even though it looks high dimensional, has so many features, it's secretly living on a smaller dimensional thing, which is its structure. Okay? So, and now turns out your denoising autoencoder starts figuring out that structure. More precisely, so if you look at your data minus your autoencoder's output, encode, decode, this is now a vector. This is the true thing. This is what your system is producing as an approximation. The difference is a vector, right? And if you make this noise like annealing to zero, like put some noise, then start reducing, keep training, eventually turns out this residue converges to log density gradient. This is called score function. What is it? Your data had a density that you didn't know. You know, it's just some data. I don't know what's the distribution of it, right? But it's got some distribution, right? And then that's the density. When you take the log and the gradient, you have a vector. This is called score function, gradient of score function, more precisely. And turns out that's where precisely the things converge. So that's what you're seeing in the plot. So if you are like close to the manifold, the density goes to the maximum. So the gradient will be zero, right? So in the maximum and minimum of your density, this function, the gradient, of course, will start being zero. What is gradient? It's the change in density. So if you're on the manifold, this is the peak of your density, gradient goes to zero, so that's why you don't see anything in that vector field. If you're far away from your data, density is close to zero this time, like what you're seeing here. That's like the lowest point of your density, then you again get gradient zero, okay? So it turns out that's what denoising autoencoder ends up learning. But in the experiments we were doing, it's hard to see this because probably you need a really huge autoencoder to actually see this. But it's good to know. So that's somehow denoising autoencoder turns out it's learning the density of your data without you know it. Okay, so go ahead, Adam, you have a question, looks like. Okay. If the question was, is this cool? I don't know. It depends on your taste, right? So, okay. So, so far what we got in this autoencoder stuff, bottleneck autoencoder, denoising autoencoder. And then there's, as usual, some regularization tricks. Some of it is specified for this business. So first trick is what's called contraction. Sometimes people even call it contracting autoencoder or something. I don't know why people like fancy names so much. So what is contraction? You have a map, you know, that takes some input, gets some output, okay? If the norm of the output is smaller than the input, you say it's contract. That's what a contraction is. So just making it smaller, basically, right? And then by norm, not the shape. And then what you say is like, you put that penalty on your encoder part of your architecture. You don't want it to make things so much bigger. So you have some loss function in mind. On top of it, you say some, you know, lambda times some matrix that represents how big is my encoder. Now the question is, what should be that matrix? Your encoder is like a neural net, right? The first matrix comes to your mind is take the gradient. You'll have a Jacobian matrix. And that's exactly what you penalize. Okay? And this is already computed by your architecture. So it doesn't give you extra computational overhead. And this turns out to be a decent trick to regularize autoencoders. Okay, that's the first trick. And the second trick is like sparse autoencoder. What is it? Instead of penalizing with the contraction thingy, penalizes L1, L2, the usual regularization we have been doing. But there's a little catch. This works sometimes, but also quite often gives a lot of trouble for reasons I don't fully understand. Okay, this trick we use all over the place in machine learning, L1, L2 regularization. For autoencoders, you get a lot of instability, a lot of errors sometimes. And then people came up with different ideas similar to this. At the end, what you want is a sparse autoencoder. You want that neural net not to use all the weights all the time when you're inferring. You want it to be more sparse. And if you're probably, I don't know, someone like this Hinton who got the Nobel Prize, like a believer of neural nets, they would claim this also is similar to how our brain works. Like we have a whole bunch of neurons, they're connected, but they don't keep firing all the time all together. Okay? But that's more political. I don't care about that. All right. So this sparse autoencoder has that inspiration as well. Okay. So at the end, if this is giving you trouble, if it works, it will give you a sparse thing. But if it is giving you trouble in numerics, etc., so there's another trick people do. They say, okay, I have some prior distribution in mind that I think represents how my data is looking like. You penalize the distance of what your encoder is producing as a distribution to your prior. That's some sort of sparsity inducing penalization. You do KL divergence from a prior that you somehow have to come up with. So, of course, this second thing is a little more sophisticated, not so easy to pull, but people have tricks for it. However, the same idea gave rise to something more fruitful in a way. It, I think, was an inspiration to what's called a variational autoencoder. So I'll tell you what that is. So what am I talking about? So it's like, don't read the equations there yet. So far what we have done is fully deterministic, right? We are training a deterministic neural net. There isn't so much randomness involved. We take the data, we train it in, we have a loss function. And we train it enough, then we just use it to represent our data. Yes, do you have a question? Yeah, go for it. So it's enforcing not necessarily lower dimension, it's enforcing less weights. So that makes your thing look sparse. So you're using just few of those connections in your neural net. That's what they mean when they say sparse. Yeah. Very good. Yeah. So like if you allow a whole bunch of weights, you start producing a divergent distribution compared to your prior. Your prior is usually something vanilla, right? You say it's Gaussian with blah, blah covariance. So you're kind of holding back your neural net by doing this. You're saying, though, don't change too much. You initialize with small weights, and then, of course, there's also some initializing big weights. So, it might so this is a way to do dimensional reduction. So far in dimensionality reduction, we never used neural nets in this class. So we used probability, we used linear algebra, etc. So now we are talking about how to use neural nets for that purpose. And the common name for this is autoencoder. Okay. So yeah. So yeah, I think now I get what you say. So the only thing we need to be careful about is like, are we reducing dimension of the data? or reducing dimension of the computation we are running. So when you're introducing sparsity to your autoencoder, you're only reducing the dimension of the how many weights you got. Basically, your computation hopefully gets easier to pull. But in terms of reducing the dimension of your data, it's coming from your architecture, essentially, right? So if you design an architecture like this, you're reducing it to this dimension after encoding. So it's not necessarily about your penalty. Yeah, now I understand what you mean. When you said dimensionality, I thought data dimension. Okay, now I got it. Okay, any other questions so far? Yeah, go for it. Very good question. And we agreed when you were not here, if you come and ask this question, you all pay, you offer all of us, I don't know, whatever people like. So, okay, just kidding. Since you are not here, you don't know if we did it or not. Okay, so we hold a vote and we said, either people were merciful, they wanted donuts. I said it's too cheap. Okay. All right. Anyway, so the reason it's called autoencoder is it's inspired by PCA. So in PCA, what do? We find the top directions by eigenvalues, singular values, whichever way we do. Then we take our data, we project it down to those D directions, but then we put it back up. Okay. And then our loss is like after putting it back up, right? Because I need to take minus of the same dimension vectors. So this lives in n dimensions, but it is a D-dimensional thing. I'm putting all my data on like a plane in 3D or on a line in 3D, okay? But they're still living in 3D. So this part is encoding, this part is decoding. Okay, no problem. Basically, people see it like a nonlinear PCA. Instead of doing linear, put your neural net to nonlinear. All right, very good. Now, variational autoencoders. So variational stuff will use also some probability inside the neural net. That's the main difference. This can be also called actually generative autoencoders. So it will have a generative capacity. So a autoencoder is something like PCA. You did PCA on your data and you ask PCA, can you sample me can you give me a sample of my data? PCA will do nothing because it's not what it's constructed for. But if you remember, we also discussed something called probabilistic PCA. It can generate a sample, okay? So this is gonna be same story. So we'll make our encoder something generative. The interesting idea there is, instead of training the decoder to take that generated stuff and put it back up in the right way, they train it or we train it to kind of invert that generation. Okay? So you start from your data, your encoder neural net here will generate some random data off of it, and your decoder will take that random thing, put it back up to how it was looking like. Okay. All right. So a bit more technical details. So what we would like to do is what stays Z is our latent thing. X is our data. Z is like the reduced dimension thing. X is the data. So this is, before in probabilistic PCA, for example, we had a Gaussian with a linear thing on the right-hand side. Now we want to replace it with whatever neural net you got here, and then some variance. Okay. So this will be your encoder, essentially. It's taking your Z, the latent guy, and if this is done right, the likelihood of seeing your data X should be high. This is the likelihood part. This is the encoder part, okay? This is how we want to train the encoder. I don't know how to turn this into an algorithm, but just talking mathy for the moment, okay? I'll talk about an algorithm trick in a couple minutes. Okay, this is what ideally we would like to do. You would like to train your encoder so that the max likelihood is high, okay? Then afterwards, you want to also do posterior, right? So what is posterior? If I saw the X data, what was the probability of that Z given by my encoder happening? That's the posterior. Okay, that's ideally what I would like to do, but I have no idea how to do that. And people apparently had this idea way early, like in the 90s. And it was called, Helmholtz machines. But they were not doing it in like a clean and unified way. So Maybe that's why it never took off. Okay, so they apparently had this variational autoencoder idea many years ago. Okay, but anyway, so the reason it was obscure is like the way they were doing it was kind of ad hoc and complicated. So now there is a more like systematic way to do this. Don't try to read all of it. I'll try to walk you through. So what you do is you say, here's my likelihood thingy, and here's my posterior thingy. You put like a penalty on trying to say my posterior should not be so different from my likelihood. Okay, somehow, right? And then what does this do for you? You just made this up. So what the heck? Okay, so you look at it and you say, okay, this guy, if you go through definition is this, and you apply Jensen inequality, turns out this guy is always less than equal to log of your likelihood thingy. Okay, so this gives you a lower bound on the thing you are trying to increase. So you want this to be big. You want likelihood to be high in your encoder. This thing doesn't do that, but it gives you at least a baseline. If this is high, this should be high as well. So instead of working on it, which we have no idea how to do, we just work on increasing this, which is a little more tractable. That's what created this variational autoencoders, basically. This is sometimes called ELBO, empirical lower bound something. Okay, algo. Evidence lower bound. Yeah, there you go. Thank you. Evidence lower bound. So basically, you maximize this. So we are used to minimizing loss functions. That's the only part that this will feel a bit different. But at the end, that's what we are still trying to do. If you take minus of this, you're minimizing, right? So if you put minus in both sides, minus of this is less than equal to that. You can as well minimize minus of this one if you really want to minimize. That's the same thing. Okay. So this is how you train a variational autoencoder. So here is a picture from our textbook, trying to explain it in a schematic way. So we are using two loss functions here, one on encoder, one on decoder, essentially. We combine them together in our loss, but one of them is acting on the encoder, the other one is acting on the decoder. So let's look at the one on the left for the moment. So this KL thingy is what I just showed you, okay? And the other blue on top is the usual loss. So your variational autoencoder produces something, and you check it against your data, okay? And you combine these two, that's your loss. Now, they do a little trick, which is called reparameterization trick, because here, your encoder needs to generate something, and you will put that generating thing inside decoder, right? Okay, so the trick is to generate that thing, you only need these two quantities, covariance and the mean. It's Gaussian. So you don't ask your encoder to literally generate something, you just learn those, and you just sample from Gaussian with that stuff, and you create it out. It apparently speeds up stuff. It's like a dirty trick, but makes things a lot easier. But at the end, this is the architecture. You put a KL on your encoders, don't deviate too much from my prior posterior difference. And then you put your mean squared error at the end of your process, and you design a variational autoencoder this way. So now the question is, of course, does it do anything better than the standard deterministic autoencoders? This looks a lot more complicated, right? So why should I bother with this, right? That's the question. So turns out there are two things about this. One is, if you need sampling, you kind of have to do this. Autoencoder cannot give you a sample. Second, this seems a little bit more robust somehow. Maybe that noise in the probability, allows you to get rid of pathological or outlier cases. Somehow variational stuff turns out to be a little more robust. So in here, you see a picture. On the left, this is visualization of something created by the variational autoencoder. On the right, it is standard deterministic autoencoder. So you kind of see the variational guy managed to pull together data from the same group a little better than the standard autoencoder. And in below what you see is something called, what is it called? Let me see, image extrapolation. So what do? You take like 2 images from your data, you do whatever dimensionality reduction you do, and you try to kind of interpolate between the 2 images, and you see what you get out of it. This is a way to see if you're able to distinguish between these 2 images well or not, for example. So in the right, you see they all look the same. So the system is not able to distinguish so much. On the right, you see it starts from here, changes slowly. So the left, this one is variational autoencoder, this is standard autoencoder. So overall, it's hard to claim variational autoencoder is strictly better, not really. But overall, it seems more robust. So if you will have to do generation, do variational. Otherwise, I would usually start from deterministic. Then if it doesn't work, go to variational, but you don't have to do what I do. You can do smarter things. So because the first one is pretty easy, you just write down standard API and just train it. The second one is a little more complicated, but not too bad either. Okay. So that's all for this autoencoder stuff. Any questions about this? So, as I said, we used linear algebra, then probability, hashing, sketching, streaming, Janssen-Lindstrauss. Now we also talked about using neural nets, autoencoders. And after this, I'll tell you more geometric ideas to do dimensionality reduction. That will be the rest of the lecture today. And I hope today to complete dimensionality reduction discussion. Next week, I'll do some other stuff. And that's our last week next week. Okay, so any questions about autoencoders? Do they look okay to you, Jordan? Like, not so bad, not so good. Yeah. That's the vibe I got from. All right, that's okay. They are pretty useful. As I said, if you're not satisfied with variational autoencoders, you can Google representation learning. That's the field that tries to develop techniques to process data that you don't necessarily know which features are important yet. Okay. And I am learning a lot of representation learning theory because of astrophysicists. I started working with some astrophysics people. There is gigantic data from stars, and they don't really know what they're looking for. So they come and ask me, can you give us algorithms that will find the structure in our star data? Okay, what is that structure, right? So, and then usually there is nothing clear comes out of our hours of discussions. I decided, okay, if there's nothing clear, let me try representation learning since it's not clear what you are looking for. All right, so the next thing I'll tell you is called manifold learning. So what the heck is manifold learning? So to use manifold learning, you need to kind of be okay with manifold hypothesis, which is your data is secretly living on a lower dimensional curvy object, even though it looks like it's living very high dimensions. Your data has got like 1 million features, but it's actually living on a 100-dimensional manifold without telling you, or maybe even less, maybe 20-dimensional manifold, okay? So that's the main idea here. You try to design algorithms that finds whatever that curvy manifold is, so that if your data is a little outside of that manifold you figured out, you just project it down. So the main idea is like, instead of like PCA was finding a best linear subspace fit, let's find the best curvy stuff fit. That's the main idea in manifold learning. Now I'll be more precise, of course. So first, what is a manifold? Have you guys heard of Earth is flat society? So there are some people who believe Earth is flat still, and they have foundations, they collect donations, you know, apparently they even could convince some NBA players to give them money, etc. It's like total bizarre stuff. And then the reason these people believe Earth is flat is if you look, it looks flat, right? But we know it's not. Right? But if you look, do you ever realize that when you walk, do you feel like the curvature of the world? Not really. I mean, maybe you guys are more sensitive, but I don't really see. You know, it actually looks flat. Okay, and that is precisely definition of a manifold. It's a curvy thing. When you locally look at it, it looks like a linear flat space. Like that's what a manifold is. Somebody should teach these people about manifolds so we get rid of Earth's flat society. Better get those $1 million to poor kids in food bank rather than Earth's flat. All right, so that's what a manifold is. So this is your curvy guy. At every point locally, it feels like a linear space. So it's if you would be fully mathy, you would say a manifold is a space which is locally isomorphic to a linear space. Anyways, so what are we going to do with this? So first off, if you have any linear map on this, linear stuff is always represented by vectors. Okay. So what kind of linear stuff I care about? Suppose I am locally looking like flat, and I have some linear thing acting on that local linear space. And we talked about this, I think, earlier. This is called tangent space, right? I talked about this. Okay, now I remember. So when we were starting optimization, I briefly talked about what's a tangent space. Okay, so this is like tangent directions here, like the velocity vectors. They're a linear space, and you can act on linear spaces with matrices or any other linear thing you want. And we know that should be represented by, again, if it is just like taking stuff in, spitting out a number just by a vector. If it is taking stuff in, spitting out, again, vectors, it's a matrix. Okay, fine. Now let's look at just the directional derivative. I have my function f, say, and I take a direction on the tangent space, and I think like if I perturb it this way, how much change is going to happen? That's directional derivative. It's a linear operation. So there should be a vector representing this guy. Normally, how do we represent it? We just take the partial derivatives, write the gradient vector. That's how you think about directional derivative, right? Take your gradient vector, nabla x, multiply it with v, you'll be done. However, here things are curvy. Are we still done with the same thing or not? That's what you need to think about. So what I'm saying is this: if you would be in usual linear world, you would say dvfx equal to this, right? And I expect to have a similar vector to this. For now, I just called it grad fx to distinguish from the usual vector we talked about. And this comes out as follows. You can go compute your good old partial derivatives, okay? But then you have to project it down on the tangent space. Then you will get this vector. Okay. So let me try to draw. Let's say this is my tangent space here. And you computed your gradient, suppose it came out like this. Okay. To get the actual correct gradient in this curvy world, you take this vector, you project it down on your tangent space. That becomes your gradient. So this will be this grad f. It kind of makes sense because everything happening on that tangent space, stuff that is orthogonal to it doesn't have much meaning, okay? All right, and we want this to happen. Why? Because we want the manifold to be a lot less dimensional than the ambient space. So we actually want a lot of stuff to get projected, ignore about stuff, still get away with it. That's what we want to do. Okay, all right, pretty good. So let's do an example. So suppose my manifold is literally the sphere, x1 squared plus x2 squared, blah, 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 equals to 1. Okay, fine. And then I have a function f. I just cooked it up right here. So by the way, first question is, what is the tangent space of a point on the sphere? Suppose I got an x that is on the sphere, which means it satisfies this equation. What is the tangent space at x? Usually they will denote it like this: tangent space at x of my manifold M. Well, I don't want to bother you working on it so much. So in the sphere, it comes out exactly vectors that are orthogonal to your point x. Vectors that are orthogonal to x. Okay. So the tangent space here, take your vector x, take everybody that is orthogonal to it. That comes out as a tangent space. Of course, you take everybody orthogonal to it and you push it towards x. You see what I mean? Like x times vector 0 will not give you a space that goes through x, right? It will give you a space going through 0. So you take that going through 0 thing, you push it up, put it here. That's exactly the tangent space. Everybody there is orthogonal to x. Okay. It's basically like this. Let me be more precise. The tangent space comes out as vectors v such that v minus x is orthogonal to x. Okay. So if you have a v here, v minus x is orthogonal to x. There's like a right angle right there. Fine. Then this is my function. I just cooked it up. I take the gradient vector in the usual way, partial derivatives. Partial derivative of x1 squared will be 2 times x1, 2 times x2, 2 times xn. And here I'll get 2x1, x1, just 2. Another 2, another 2. So the gradient comes out as follows. 2 times your vector x, which means x1, x2, xn, this is a vector, plus just 2, 2, 2, 2, 2. That's how the gradient comes out. Now, what was the tangent space? Stuff that is orthogonal to the same x. That means this part will be killed out, and you'll end up getting just this. Okay. And this also attests to the fact that this function does not change so much on the sphere, okay? Because it's almost like the sphere function. I just added a little bit. I was just trying to illustrate that what you compute and what actually is important may be different because you're projecting on a tangent space. Okay, fine. Whatever. Now, what's the Riemannian manifold? It is a curvy object like this, where you look at the tangent spaces and you move them around. The inner product on those tangent spaces also moves around smoothly, okay? So what am I talking about? Like I got a linear space right here, right? Or let me go to the picture in the beginning. So in this linear space, everybody orthogonal to this is being killed. I'm just looking at that linear space. And now I have another one here. What is getting killed has changed, okay? So the point is that change should be smooth. It should not be just jumpy. That's what a manifold is. It's smooth, right? So if it is like a discrete curvy thing like this and then jump, that's not a manifold. Yeah, that's basically what a manifold is, and that's what we are trying to fit to our data in this manifold learning business. So here's an example. Swiss roll data on the left. Yeah. So you want a nonlinear object that fits to your data well, and it should be lower dimensional than the space they are living in. Manifold is more or less what we can try to handle somewhat efficiently, and I'll make this more precise in the rest of the lecture. For now, it's probably looking abstract, very normal. It'll become more concrete. Just bear with me, maybe 10, 15 minutes, okay? Right? So why do we care about this? If we can compute with this thing, and if we can visualize our data better, if we can do dimensionality reduction better, why not? And now people are using this all over the place. I listen to talks from people who work on genetics using manifold learning. You know, it's all over the place. So it's not like a hammer that solves all the problems, but it's a decent toolbox to be tried on. And now there is a lot of good packages. I'm surprised by the open source community around this. There's a lot of good packages always being developed. So then it's just very easy. You just go to those packages, try it out in your problem, and see what you get out of it. All right, so let's get back to our discussion. So that's what a manifold is. And then on the left, what you're seeing is visualization of a data set called Swiss roll data set. Okay. So it literally looks like a Swiss roll, and you kind of see like it's like a sheet in 3D. And if you get a data point from this collection, if this is your training data, if it is not looking on that Swiss roll, you know, I can just still assume it's on the Swiss roll, project it down, and don't get so much error out of it. All right. So now I'll tell you one by one techniques to come up with this kind of manifolds to fit your data. Before I do those, I want to remind what was a positive semi-definite matrix. What was a positive semi-definite matrix? Anybody who remembers? PST, what does that mean? Huh? Yeah, so eigenvalues should be non-negative real numbers. Exactly. Or in other words, if you take this matrix, multiply it from left and right with the same vector, the number you will get will always be a non-negative number. That's what a PST matrix is. And that kind of stuff shows up when you are trying to do dimensionality reduction. For example, this is what we were using in PCA, right? We were taking our data, doing X transpose X. That was giving us that covariance matrix. We were looking at the eigenvalues, etc. And here, if you look at every single entry of this matrix, it is created off of take a data point, another one, take their dot product. That's what this covariance matrix looks like, right? Okay. Keep this in mind. We will keep using it. So first, the easiest thing to do, suppose I don't want to deal with curvy stuff. I just want to fit something linear and flat. People call it multi-dimensional scaling, but this is exactly the same thing as PCA. Okay. So I just tell you because you might see it here and there. It does more or less PCA for you. Because what is PCA? You're trying to find the best fit d-dimensional flat thing, right? That's what PCA is. And you end up, if you see multi-dimensional scaling anywhere, that's essentially PCA, okay? So this is the beginning of the story. And then what's next? The next thing is called metric multi-dimensional scaling. So I'm just telling you what people use because you might need to know these words to use a library, okay? So the next thing is like, I want to do something like PCA, but I don't necessarily have to do linear. What I do care about is like, after you do your dimensionality reduction, your data xi becomes zi, your data xj becomes zj, and your loss function is they should not differ so much. You're trying to preserve pairwise distances, potentially using nonlinear dimensionality reduction. Okay. Beginning of lecture, we were talking about Johnson-Lindy-Strauss, where you're doing something like this with probabilistic tools, right? You're creating a random matrix. It is preserving most of those pairwise distances. But Johnson-Lindy-Strauss has its limit. If you have n data points, it can only go to log n divided by epsilon, something like that. Well, you want to visualize your data. I cannot visualize like 10 dimensions, right? If I really have to go to 3D, then maybe I could try this with 3D and allow it to be nonlinear. I will make that nonlinear part more precise. Bear with me, okay? And people also sometimes do non-metric PCA, non-metric scaling, but this gets very hairy very quickly. So unless you really want to try this or really have to do it, I would say don't do it. So instead of that distance minus distance after dimensionality reduction, you also allow yourself to put whatever function on that distance. And they would usually alternate between finding the best function versus finding the best fit of dimensionality reduction, alternating minimization type stuff. As you can tell, this gets very complicated very quickly. You're allowing a lot of functions, also a lot of different dimensionality reductions, and you're trying to find the best pair among those. Okay. All right, so this is non-metric PC scaling, multi-dimensional scaling. And metric applied to that Swiss roll is illustrated in front of you. You're reducing that 3D data to 2D. And you more or less preserve the structure, as you see. Okay, now, before we move on, let's go back to Adam's question. Why do I even care about manifolds? Right? I was okay with PCA. Or I was okay with this random matrix projection. Flat length is good, right? So one answer to that is, suppose this is your data and colors represent different groups. You're trying to do classification. Whatever linear projection you do, try to imagine this in 3D. You can never unravel this with linear stuff. You have to kind of unknot this nut. Okay. So you have to do nonlinear. So linear is good, but it has its limits, basically. Depending on your structure of your data, you know, you kind of have to do nonlinear. And Give me a sec to see if I can solve this up. Yeah. This is a very nice post. I'll share it on Canvas, obviously. No, not this one. There are several very nice. Yep. Okay, I didn't get what I wanted, so I'll probably not try searching more. So there is very nice illustrations that is already implemented. I was going to show you some real data sets that looks like that, not one way or another. But I couldn't find it, so let me not do it. I'll go back to my presentation. Okay, the motivation is depending on your task, linear may not do the trick. So we are trying to do nonlinear in a kind of principled way. Okay, so what kind of manifold stuff we could do? Okay, so what do you really care about on a manifold? Okay, let's say I got my data and I think they are living on some curvy manifold. Here's one of my data points, here's another one. One thing that changes for you is like if you have a dot here, let's say this is my dot, and another dot there, what is the easiest way to go from A to B? Line segment, right? Just draw a line segment starting from your A to B. That's the quickest path to go. That changes when you're curvy. You cannot just take the line segment because that line segment is probably not inside your curvy thing, okay? Then you start thinking about, okay, what is the quickest way to go from my data to another data on the manifold? That becomes your distance, okay? Now, how do I do this computationally? You take your data, and one way that is commonly done and usually works fine is you pick a number k, 3, 5, whatever your k is, and k is the number of relevant data points to a single data point. You're defining the neighborhood, okay? So you say, how many neighbors are important for my data? You pick that k, and then you fit, what's that? I'm sorry if I messed it up, okay? Okay, good. I thought it's like an earphone. All right, so what you do, you fit a k nearest neighbor graph to your data. For example, here, everybody's got what? Everybody's supposed to get 3 edges, but some of them apparently has more than 3. After you fit in your graph, when we see a graph, we kind of know what is the quickest way to go from A to B. You pick a node on your graph, and you run whatever algorithm you remember from your algorithms class for finding the shortest path between 2 dots on a graph. And that becomes the metric on your manifold. Okay? So literally out of the graph, you are trying to see the manifold already. You're saying, okay, this k nearest neighbor graph gives me a notion of distance. And then there are some examples here. So for example, it is saying if I would do usual distance, going from 1 to 6 would be shorter than going from 1 to 4. It's just right here. But if you care about that manifold structure, 4 gets closer than 6. Yeah. So it changes the notion of distance. And after you fit this metric, you just do your metric scaling. You can fit using whatever projection you would like. You can use a neural net, you can use whatever. Okay. That's the first thing to do, and this usually does fine. Now the question is, when can this run into trouble? Like something like this, for example, will give you trouble. If your data supposes this, right? It'll be super sensitive. Like, going from this to there on the manifold is a long path, but here, actually, they're pretty close to each other. So it's very hard for your computer to detect this. So it can run into issues depending on the shape of your data. Okay, now here's a general idea called kernel trick. Probably we'll do most of it today and maybe keep talking about it in next lecture. Because this is used not only for dimensionality reduction, for other purposes as well. Next week, I will talk about kind of more classical machine learning stuff. This was used there already for maybe, I don't know, 5 decades. Okay. So next week, I'll talk about, say, what's called example-based methods, like this density estimators, etc. There, this kernel method also comes in. Okay. What is a kernel method? So basically what you're trying to do is this. We got our data. We were doing it like a matrix, and we were taking that matrix and transpose with itself in our PCA. And every entry in this matrix is what? Take one data, take another, dot product. This is how they look, right? So now what we are going to allow is like, I'll have a kernel, which will take 2 of my data points, and will spit out a number. It doesn't have to be that product. It could be something nonlinear as well. That's the main idea in this kernel stuff. I'm going to tell you more. You allow yourself to use a function that pretends like the dot product, but when you allow more flexibility, your PCA all of a sudden gets nonlinear. Okay, I'll tell you what this means precisely. So for the moment, what do we want from this kernel? The numbers it spits out. If I put them all like a matrix, imitating this matrix right here, suppose I create my n by n matrix of the kernel entries. I want that matrix to be PSD, positive semi-definite, because that's how that X transpose X comes about. Okay, and then if it is positive semi-definite, there is a theorem 100 years ago. Somebody was working on this without thinking at all about data analysis. It was, I think, probably a mathematician or a physicist. Okay, so the theorem, I'll show you the precise statement, but let me tell you what it says with words first. Okay, I'll show you the math. Okay, so the theorem says the following. Suppose you come up with a kernel, and when you put it out, it gives you a PSD matrix, right? But the kernel could be arbitrarily complicated. I have no idea what the kernel is doing. Okay, so the theorem says if your kernel is actually like a PSD guy, it actually comes from an embedding. That's what the theorem says. Whatever kernel you could cook up, which gives you a PSD matrix when you put it on your data, is secretly an embedding model. That's what this guy figured out without knowing any of this first, probably more than 100 years ago. Okay, so secretly what's going on is like without you seeing it, it's embedding it to maybe a very high dimensional place, or it's doing some embedding, maybe low dimensional. And then, instead of taking xi dot xj, you're actually taking xi embedded somewhere, dot xj embedded somewhere. That's what the theorem says. If you want the precise mathy version, here it is. So at the end, what's going to come out is like your data will have some embedding that realizes the kernel. That's what the theorem is. What's that embedding? Does anyone want to learn the actual precise statement? Let me see. Oh, well, looks like, yeah, some people like pain. What does it say is like, you got some function, okay? And you define this operator on your functions, which does the following. Takes X, puts the kernel with another data S, and goes through all the such data. For now, I'm writing it only with one variable to illustrate the same thing in multiple variables, okay? And you integrate, that's the operation. It changes your function, okay? And this operation has like an eigenvector basis. There is some eigenfunctions for this guy. They don't change on this operation. And you could decompose every function using those, and they give you the embedding, turns out. Okay? But that's not really important, because we will try to avoid computing this embedding by all means, because it's computationally very heavy. We just want to use the facts without computing those embeddings. Okay, very good. Now, some some kernels, this is called, I guess this was a French person, probably Marseille, but I don't know, say Mercer. Yeah, in a way, exactly. Exactly. That's right. Very good observation. That's why this kernel stuff existed for many years. People were thinking about it like kernels like a density, that they were trying to fit kernels all over the place, etc. All right. Now, some kernels, a common one called, I again forgot why this was called ARD. This usually is done by electrical engineers, this type of word. So I forget. Okay. So what is it? It is like you pick a diagonal matrix, right? You invert it, you multiply, raise it to the power E. It's like a Gaussian thing. That's one of those kernels that is available in all the libraries you use. And now here are some plots. What we are doing here is like, we are taking, I think, 2 data points and putting them in the kernel, and whatever number that kernel gives, we are plotting it out. I'm only showing you these pictures to tell that this kernels allows you to create those manifolds and fit them. Okay. Since kernel is nonlinear, it's actually encoding some curvy stuff. Okay. You may not think about it this way, you don't have to. You just want to compute with them. But this is a way to do what's called manifold learning. Okay. All right, fine. Now I have like 3 minutes. I'll do something, then we will go for the rest next time. So the first thing people would do with this is something called kernel PCA. Okay. So what I want to do is this. Instead of the matrix in PCA, which was given by dot products of my vectors, I'll use my kernel matrix and try to do an embedding using it as a loss function. That's what I would like to do. Okay. Let me try to see where did I write this more precisely. There's a lot of math coming into here, but okay, I think this is good enough for today. So what we want to do is you're still going to do your algorithm will look like your PCA, but you pick a kernel, or you could try to learn the kernel from data. That's a different story. You pick a kernel and you use that kernel matrix instead of your PCA matrix. So then it looks like, since every kernel is secretly an embedding, what we're doing is actually we are embedding them somewhere, then projecting them down. Okay. That's actually what's going on in the backend. But we will never compute that embedding. We will be able to compute everything off of just the kernel. That's the tricks I will have to tell you next time. Okay, we are almost out of time. So next lecture will continue a little bit from this kernel PCA. And what else? Some more tricks on the stuff, and that's about it. Okay, probably half an hour next time. We will continue kernel PCA and some more manifold learning or nonlinear dimensionality reduction. And after that, we will move on to classical techniques, classical machine learning, which is still useful to this day.